Hello guys, welcome back to my YouTube channel. Myself Girish BB. Currently I am studying in Sri Venkateshwara College of Engineering, Bangalore. Branch ISC USN 1VE 22A017. The subject is Maths for CSE stream. The topic Poisson distribution. Let's discuss about the Poisson's distribution. First, we should go to the introduction. The Poisson distribution is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time or space when these events occur with a non-constant mean rate or independent of the time since the last event. Probability mass function means PMF. The probability mass function of a Poisson distribution is given by P of x equals k equals k E minus lambda k, where k is the number of events that occur in a fixed interval. Lambda is the average rate of occurrence of the event within a given number. E is the base of the natural logarithm approximately equal to the 2.71828. Then characteristics. Discreteness. The Poisson distribution deals with discrete random variables, meaning it's used to model events that can only take on integer values like 0, 1, 2, 3, etc. Count data. It's commonly used to model the number of events occurring in a fixed interval of time or space. This makes it suitable for scenarios where events can be counted, such as the number of arrivals at a service point, the number of phone calls received in a call center, or the number of defects in a product. Single parameter. The distribution is characterized by a single parameter, lambda, which represents the average rate of occurrence of the events within the specified interval. This parameter defines both the mean and the variance of the distribution. Independence. It assumes that events occur independently of each other. The occurrence of one event does not affect the occurrence of another event. Mean and variance. In a Poisson distribution, the mean, mu, and variance 2, are both defined by the parameter lambda, which represents the average rate of occurrence of events in a fixed interval. The mean and variance of a Poisson distribution are both equal to lambda. Mathematically, this can be expressed as mu equals lambda 2 equals lambda. Here mu represents the mean and the variance, and the lambda represents the parameter of the Poisson distribution, which is the average rate of occurrence. So if you know the average rate of events occurring in a fixed interval, you can directly use it to calculate both the mean and variance of the Poisson distribution. This property simplifies the characterization of the distribution as both as the mean and variance determined by the single parameter. Limitations. Rare events. The Poisson distribution is most suitable for modeling rare events, where the probability of multiple events occurring in a small interval is negligible. If the occurrence of events is not rare, other distribution like the binomial distribution may be more appropriate. Underestimation of variability. The Poisson distribution assumes that the mean and variance are equal, lambda. However, in some cases, the variability of the data may be larger than predicted by the Poisson distribution. This can lead to underestimation of the variability in certain situations. Applicability to continuous phenomena. While the Poisson distribution is commonly used for count data, it may not be suitable for modeling continuous phenomena. For example, if the number of events per unit interval can take on any real value rather than just integers. Other distributions like the exponential distribution may be more appropriate. Then sensitivity to assumption. Like any statistical model, the occurrence of predictions, the Poisson distribution is contingent upon the validity of its underlying, as deviation from these assumptions can result in accurate predictions. Applications. The Poisson distribution finds applications in various fields due to its ability to model the occurrence of discrete events over time or space. Some of its key applications include queuing theory. Poisson distribution is extensively used to queuing theory to model the arrival process of customers, jobs, or entities into a system. It helps in analyzing waiting times, service capacities, and system performances in areas such as telecommunication, transportation, and customer service. Telecommunication. In telecommunication, the Poisson distribution is used to model the arrival rate of calls at a switchboard or call center. This enables telecom companies to optimize resources, predict call loads, and design efficient call handling systems. Then next, insurance. Insurance companies use the Poisson distribution to model the number of claims received within a specific time period. This helps in estimating the risk exposure, setting premiums, and managing claims processing operation effectively. Epidemiology. In epidemiology, the Poisson distribution is evolved to model the disease, infection, or other health-related events within a population over time, studying disease outbreaks, estimating infections rates, and evaluating the effectiveness health interventions. Assumptions. The Poisson distribution relies on several key assumptions. Independence. The occurrence of events must be independent of each other. This means that the probability of an event happening at any given time or place is not affected by the occurrence of previous events. Fixed interval. Events are counted within a fixed interval of time or space. The interval must be clearly defined and consistent across observations. Constant rate. The average rate of occurrence of events remains constant throughout the fixed interval. This assumption is often expressed through the parameter lambda, which represents the mean rate of events. Rare events. The probability of more than one event occurring in an infinitesimally small interval is virtually zero. In other words, events are considered rare relative to the interval being to lake. Discreteness. The Poisson distribution is appropriate for modeling discrete events that can be counted as whole numbers 0, 1, 2, 3 like this. Then advantages. The Poisson distribution offers several advantages. The first, flexibility, simplicity, mathematical properties. Flexibility. The Poisson distribution can model a wide range of phenomena involving the occurrence of discrete events, make it applicable to diverse real-world scenarios. It is particularly useful in situations where events can be counted. Simplicity. The Poisson distribution is characterized by a single parameter lambda, which represents the average rate of occurrences of events. Mathematical properties. The Poisson distribution has well-defined mathematical properties which facilitate statistical analysis and interference. Real life example: arrivals at a coffee shop, arrival of an email or text message, accident at an insertion. First example, suppose you are running a small coffee shop and customers arrive randomly throughout the day. The number of customers arriving within specific time intervals, example every 15 minutes, can often be modeled using a Poisson distribution. This helps in staffing decisions, inventory management, and predicting peak hours. Then uses of engineering life, reliability and maintenance planning, traffic engineering and transportation system, quality control and manufacturing process. Engineers use the Poisson distribution to model the occurrence of equipment failures, component breakdowns, or system malfunctions. By understanding the distribution of failure events, engineers can develop effective maintenance strategies, schedule preventive maintenance activities, and optimize spare parts inventory. Summary: the Poisson distribution is a discrete probability distribution used to model the number of events occurring within a fixed interval of time or space. It's characterized by a single parameter representing the average rate of occurrence. The probability mass function of the Poisson distribution gives the probability of the observing a specific number of events in the interval. Key properties include independence of events, the rarity of events, and its applicability to count data. Conclusion. In conclusion, the Poisson distribution serves as a fundamental tool in probability theory and statistics, providing a powerful framework for modeling the occurrence of discrete events over time or space. The Poisson distribution remains invaluable in various fields, offering insights into its continued relevance underscores its importance as a cornerstone in statistical analysis and probabilistic modeling. Thank you for watching my video.